All right, that's time. Yeah. All right, I think today is feeling to me like a stretching day. So, come stretch with me. Come stretch with me. Don't let me be awkward up here on my own. You can sit down and stretch if you're feeling it, but just do whatever stretch feels good. Wake up a bit. You know, I want high energy today, I guess. That feels good. That feels good. I like it. All right, so backpropagation. I'm doing another talk on backpropagation. I decided, so first off, no more live coding. Way too stressful, way too little help. What we're going to do instead is that I asked the TAs, and we might be getting a new TA, to do office hours specifically for coding help. So look out for those and go to those if you need help with the coding. In class, we're going to focus on more abstract concepts, and I will try to be more precise. Today, the talk I'm going to give is going to be the most mathematically precise, so all the things are going to be completely correct. You could just rip them from here to use them, which I haven't been doing. Just help out. It's just me being a little bit more proper, but it's not going to be any more difficult to understand. Okay, so, also one more thing is future homeworks, I've also made the decision, are going to be in a different format. We're going to do notebooks. So if you've ever used a notebook before, it lets you run inline and it lets us have the instructions in place. I think it'll be good, but we don't need to discuss the homework for 30 minutes at the beginning of this lecture too. Anyway, so backpropagation. Let's start with a little bit of recap. We haven't talked in a little while about where we are in terms of what we can do. So let's use this recap slide again and just talk about it. So remember, we wanted to fit some data in some way, and we started by looking at linear models. So we've only really looked at linear models, but we have now started. So we had just some line of fit, and we realized there were multiple lines, right? You all recall. There's multiple ways that we could best fit it, depending on what we mean by that. So exactly, we define what we mean by that. And in the case of this, we say that it is, mean squared error, which is just the difference squared of each of them. Hopefully this is entirely a recap for people, but hopefully it'll get us on the same page. And we also realize that by defining it this way, saying this is what we care about, and minimizing this means that we do better. So this is our paradigm, and then we realized that we had the gradient. So if we look at our loss function as a curve here, as some three-dimensional shape with respect to our parameters, we realized that we can think of our current setting of our model as some space on that curve. And we also know some mathematical theorem that is going in the direction of steepest descent, which is the gradient, will necessarily, if we take a sufficiently small step, increase our loss. And likewise, taking a step in the negative gradient will necessarily decrease it. So that's set up for it, and then we came up with this equation for gradient descent. We just move in that direction. But then we realized that it matters what magnitude we have. If we have a small magnitude or a correct magnitude, then we might end up at a very good local minima, but we could have too high of a magnitude of our gradient, and then we'll jump and we might hit some higher loss, or we might go out of this minima entirely. We might never settle. We might just bounce around. So we adjusted our equation and introduced the learning rate hyperparameter. Hyperparameters being a whole new concept for us, which was things that we change outside of the model changing things. They're parameters that we set, not the model. And we will explore in the future more how we decide what those are. In the homework, we try a little bit of that. And you'll see, but we have better ways of doing it. Anyway, so that's that. And we used the Perceptron as our model, right? Everyone loves the Perceptron, right? Which was just the weight matrix multiplication and then adding bias, which was exactly this. And we also realized that we could include a threshold in it to do classification. This is turning the output from being some continuous value into some binary value in this case, but some discrete value in general, which allows us to classify yes and no. And we can use this to simulate circuits or different logical gates, or to hypothetically classify if something's a cat or a dog. We can do things like this now, just by adding this little threshold. So then we looked at computation graphs, and I'm going to go through a computation graph of this. So part of the reason I'm repeating the computation graph talk about this is, one, I think I can do it better this time, and I think there's more information that I think will help with the whole story of what's going on in homework 2. And 2, I made the math a lot more precise, so all of the things that I put in here you could exactly take and use in your code. So if you are struggling, this might be helpful. Anyway, so we had just this, and we realized that all we're doing is we're multiplying these like values, right? Each of the weights with their corresponding input, and then we're summing them all up. And we realized that we can take the derivative of this with respect to each of our weights by going backwards through the chain, which doesn't really matter for us in any reason yet, but once we include a loss function, which here is just mean squared error, we can again label all of these and then take the derivative going all the way back through the chain. And by doing this, we can take the derivative of any function, our model included, right? It's not a very, it's a pretty naive way to find the gradient, because we'd have to calculate the derivative for each of these, but we can change that, and we'll see that in the future of this lecture. I also want to clarify, I'm going to use a different notation now for the dot product. Before I was doing W transpose X. Some people did not like the transpose, and I think it was confusing a lot of people with the dimensions. Here I'm going to say X dot W. This is more appropriate with the way that the homework is structured, and it's a lot simpler for you guys. So that's a call that I've made. It's the same thing as all the notations we said before for it, but this one is simpler, and in code it would be X dot dot W. So it's very easy to translate. Okay. So we had this, and again, we realized we can go back through the chain. Just a reminder so you guys can see it. We go backwards through it, through all of these steps, and then we calculate the derivative of this. This is all just, again, still recap. So do people, how many people, let's do thumbs up and thumbs down. How many people remember all of this? All right, cool, cool. All right. I think it's still good to refresh your brain just so that, remembering that you remember it is pretty good. So then we decided we want to do a bigger model. We justified this by saying that we actually realized that sometimes more layers of our network is stronger. We realized this by looking at the XOR gate, which is unsolvable by a single layer, but is solvable by multiple layers. So we came up with this naive construction here, which is just, and again, you can see I changed the notation here, a double dot product. So we just do a matrix multiplication, then a matrix multiplication, and that's it. We did realize, so I'll talk about this in a second actually, but we can do now a little bit of a notation change. This is the notation change we already did, but I just want to reintroduce it. This was what we had for a dot product, and when we did a computation graph, it looked like this. But since we already know how to do the derivative of a dot product, we can just make it a single operation. This is really useful for us because now the computation graphs don't have to be so complicated. And this is where I've gone at when I've said that the computation graph is a tool for you, is whatever functions make sense for you to use that you know the derivatives of, use them, all right? When you're doing it by hand. We'll see later what we have to do for computers. So then we realized if we wanted to have a multi-layer perceptron, we could just, we know the derivative of this, right, is x. That's something we've established very well. We realized if we change them together, we get something like this, right? So now that's the operation. And I want you to take a minute, right? So this is to test how much you remember from all of this. In small groups, try to come up with the derivative of this for 5 minutes, all right? Go. And I want you to also pay attention to the dimensions if you can. There's partially right answers where you don't care about the dimensions, but they are wrong in terms of coding. So try to pay attention to the dimensions. All right, I think that's about enough time for people to think on it. So let's start with a sub-problem of the problem here. So we first want to take the derivative of the output of this entire thing with respect to the output of the first layer, right? So we can see that there's two derivatives. If we care about finding the derivative with respect to W0, we have to take it from the endpoint to here. There's one jump, and then from there to there. You can't really see my pointer. That was unhelpful. But we want to take it back through the chain. So what is the first derivative from the output here to the output of the first layer? W1. W1? Very, very close. So let's say it's W1. All right. So then what we realize is, if you recall, I've said a lot of times that when we take the derivative with respect to something, we want that derivative to be the same dimensions as that something. So is the output of the first layer the same size as W1? It isn't. So this is where a little bit of a nuance comes in. And this is only going to happen when we are not using, or when our final operation is not an element-wise operation. We'll see later that isn't a problem sometimes. But what happens is we have to multiply this now. So this is the first bit. That's actually the, I did it in the other order. But this first bit right here, the D out that I have there, so you were completely right that it is W1. It's actually going to end up being W1 transpose, right? And don't get confused with, like, before when I used the W transpose notation, that was to represent a dot product. But we do have that in our derivative, sometimes we need to take a dot product of something transpose. This is to make the shapes line up. So essentially, what that D out is, and this is just, like, the reason I call it D out is that it is the derivative of the output with respect to the output. And what should that be? 1. But importantly, what shape is it? So it is the shape of the output. So this is the shape of the output of the second layer. So if we take the shape of the output of the second layer and do a dot product with the second layer matrix transpose, essentially what it's doing is undoing the operation that W1 did. So when we do the transpose, we're changing the dimensions, right? And then we are undoing the dimension change so that it goes back to the same size as the output of the first layer. All right, how much does that make sense? Confusing? I know, I get that. It is a bit confusing. So the reason I call it D out is that it is the derivative from whatever we care about back to that point, whatever it is. So derivative of the output. In this case, it happens to be itself, which is confusing. Maybe, would people find it helpful if I drew out the dimensions at all, like on a piece of paper? All right, I'll do that. Got to set this up, though. All right, shouldn't be that bad. OK, let's see. Cool. All right. So let's draw the computation graph on the piece of paper. Oh, man, that's stuff bleeding through. I have paper over here. Give me a second. Always keep paper on me. All right. So let's draw out the computation graph. So let's say that we have our x and our W0 going to something. I'll draw it like that box. And then going to some W1. Again, we do a dot product like this. And let's label these, just for the sake of it, of A and B. Okay? So first thing that we actually care about finding is the derivative of A, or derivative of B, sorry, with respect to A. And then we're going to multiply that by the derivative of A with respect to W0. That's how we get the chain, right? So what we see is we're just doing a dot product here of the operation B is just going to be A dot W. Oh, yeah, sorry. Thanks. It really doesn't show. Maybe I can zoom out, can't I? There we go. All right, 0, 1, W1, right? And let's look at all the dimensions of everything. So we're going to label the dimensions sort of arbitrarily. So let's say that x, and I'm going to use two-dimensional dimensions here. So let's say this is just some a, b, right? And now we're going to say that we are using some weight matrix that is size BC, okay? So this is essentially exactly the kinds of dimensions that we're dealing with in homework 2, right? We have some two-dimensional input, some two-dimensional weight matrix. And what this will do is this will change this from an AB into an AC by a rule that we established last class, which was when we multiply these, the center terms cancel out and we just get the end terms. So now we have some AC, and now let's say that we have some CD here, right? So we want some output size of AD is what we're going to get now. So this is that. This is now going to be some AD. Okay? I mean A by D matrix. So somehow we would like to take this derivative in a way that that keeps the shapes. So the shape of our A, right? So we need to get the output of this to be of the shape A, which is an AC. And we know that the derivative of this operation of a dot product is just the weight matrix in this case, right? So if it's a dot product, you just take, it's essentially multiplication. You just take the other term when you're taking a derivative. So in this case, this would be W1. That seems reasonable, because we're just doing, that is strictly what the derivative would be if we didn't care about dimensions. The problem is that it is a dimension, that matrix right here, W1, is going to be of size, I erased it for this, but of CD, all right? So we somehow need it to be a derivative of that size. And the natural way that we actually do that is we want to use, we're multiplying it intrinsically by 1 because we have some derivative of this term to itself. This is something we don't need to worry about when we're doing derivatives with scalars, but we do with matrices. So what we actually want to do is multiply it by some matrix of 1s in such a way that we end up with the correct dimensions. That happens to be this shape. So we take this shape, or it will always be that shape because we're undoing that operation. So we take that shape, so we have some set of 1s that is that shape. So let's just say some matrix of AD, right? It's a matrix of 1s of shape AD, right? And how do we multiply the other matrix in such a way, the matrix W1, such that we end up with a shape of AC? We multiply it by the transpose, or dot product it, if you prefer, by the transpose of itself. So, or transpose of W1. So this will be dot W1 transpose. And this will give us a shape of AC. And this is the correct answer for how to calculate this derivative. This is a nuanced point that you think might not be important, but is very important in being able to figure out how to calculate the derivatives, which you're having to do in homework 2. Things like this probably trip you up quite a bit. This is one that, yeah.
So if AD is AD the dimensions of W1?
It's the dimensions of the output. So it's the same dimensions as the output. So this is a matrix of 1s that is of shape AD. So it's just 1s in the shape of AD. The reason we do this is because we're multiplying it by this transpose to get the right size. It is technically the right thing to do. Yeah.
So it's all 1s, it's not like an identity.
Yep, exactly. Okay. Exactly. Isn't that strange? But it is correct. So that's a bit weird, but it is the way that you could maybe justify it like intuitively to yourself is you are first taking the derivative of the last element multiplied by itself, if you'd like, or with respect to itself, and that will end up with the correct size and will be all 1s. Another way you could think of it is that we just, I guess we have to start with the end shape when we're taking this derivative. We have to take, we start with this shape of B, and then we have to end up with that shape A. And so we start with this shape AD, which is the output here, and we start by multiplying by that dimension of 1s. Again, a weird nuance point that doesn't come up exactly in homework 2, but I think is, you can immediately see how it can become a problem if you don't understand that when you're trying to calculate some of these derivatives. Anyway, not particularly important that you know this for homework 2, right? But it is important to tell the story that we're doing in the lecture right now. And it will be helpful to see things like this often so that you can think about these in a new way. All right. Yes?
So we're multiplying this for the computer, right? For the algorithm, the reverse order?
Yeah.
Okay.
Oh, yeah, like what? Yeah.
And to
from x and w0. So
to calculate A and B, we would need x and w0, and then we move forward.
yeah, so we'll do the proper backpropagation algorithm later in the lecture, and I'll clearly explain it then.
Okay.
Don't you worry. But we have to, at the moment, we manually do all of this.
Okay.
We'll see. All right. Anyone else want to ask any questions about this? It is a weird nuance point, and I get that thinking about these dimensions is probably the hardest part of this class, right? Which I know, but once you get it, you do get it, usually. I think it is something that takes a lot of time to understand, but once you have understood it, you will be able to use it. It's sort of like understanding like basic math operations. Once you add this to your dictionary, you got it. All right, so let's go back to lecture. So we have this now, and this other matrix multiplication, very nice. We can see that the dimensions end up working out. If we actually look at the dimensions of everything like we did before, all of these dimensions add up to the exact dimensions of W0. All right? So again, this is me being a little bit more proper with my math, so you can see exactly this is the operation we're doing to get the correct dimensions. Just so you aren't confused trying to just copy and paste what I write in class. This is exactly right. Anyway, now, let's look at an arbitrary one, all right? So if we look at some arbitrarily many-layered neural network like this, what we realize is it does have a sort of repetitive structure, right? And we'll throw it through the loss here. And when we go to calculate one of these, we end up seeing that we just go backwards through the entire chain, right? So we don't care about calculating any of the intermediate weight derivatives. And we see that we can just go through the loss to ON, and then backwards through this entire chain. So we just multiply it by derivative ON over ON minus 1, so on, until we get to where we care about. So this is one of the main things to see about having this repetitive structure like this, is we can just go through this chain. It's one of the main reasons why this standard, this multi-layer perceptron standard, has stood the test of time, is that this is very nice for a reason we'll see soon. All right? Yeah, and we see for some particular WI, we end up going through here, and we just stop where we want to, and then get off, and just multiply by that new derivative to go to that weight in particular. So we can just go up the chain, get it. And then if we want to get the next one, you go up the chain, get the next one. Right? That is a bit wasteful, you might realize, and that'll be for later. All right. I forgot about that. All right. So just to recap again, nonlinearities, right? Why do we have them? Anyone? Short answer. Why do we have nonlinearities? I'm going to wait for someone else. Why do we have nonlinearities? Someone else. I want to hear from someone I haven't heard from yet. I like to get to know people. Sure.
Linear functions are not complex enough to present everything, so
That's true, but why don't we just add more layers?
Because then you could just make a one linear.
Exactly. So if we have multiple linear operations, or affine operations in general, then we can combine them into a single affine operation. So this is just, they are exactly identical computationally power-wise. We can just take two matrix multiplications, combine them into a single one with dimensions that are combined. And we can do that. We can actually construct that matrix. And as I said before, it's true of any affine operation. Nice. Affine, by the way, I don't think I have well defined. Affine is a linear operation that does not necessarily go through the origin. So that means it could have a bias term, is really the only difference. Cool. So then we learned that we can add some nonlinear function, right? And that will make it not the same. And then we realized that we have multiple different good contender functions, right? So we have sigmoid, which we learned about, that has this derivative. This is what we're going to use, and this is what we're using in the homework, and this is what we're going to use in a minute to actually go through all that. And we had ReLU, which was turned out to be the best one. Does anyone remember why this was bad? I know we did a Kahoot on it yesterday, or not yesterday, on Monday. But who can tell me the number one reason why this is bad? Yeah.
No negatives.
No negatives. I wouldn't say that's the number one, but it is a downside. Yeah.
When the value of x is larger, smaller gradient,
So that ends up being a bigger problem for us. They're both issues, but that ends up being the biggest problem for us. TANH does the same thing, which is not great. And ReLU kind of does the same thing, but turns out to be fine. It really is like weird. And people have tried so they have this just 0 for anything negative. People have tried creating a slight negative slope, right? So that still is technically nonlinearity, even if you get it very, very, very close. And it does not outperform this, which is a weird thing to reckon with. Anyway, if you have any ideas on that, like I said before, open problem. All right. So now let's look at our computation graph with nonlinearities included. So as I saw before, I use this sort of O and A notation, right? So this is the output of this layer, this is the A of this layer, right? And we will repeat this structure like this. And the main point that I want to raise is there some way we can abuse the fact that this is repeating to save ourselves time? Anyone have any ideas? Give it a little think. Think about how we could use the fact this is repeating, right? We do the same 2 operations over and over and over again. How might we abuse that to do something make our lives easier? You can talk to each other. What? Can I repeat the question? All right, I'll repeat it to you. I guess that people already. All right, all right. I want to hear from you guys. I want to hear. So, anyone have any ideas? There are definitely some good ideas floating around. Yeah?
Is it because if we want to get like the derivative of W1, we know we're going to need to calculate the derivatives of the previous values first, and then it's just going to be like a multiplication chain. So if we just store those values each time, we won't have to recompute them.
So that is absolutely a good point. It's not exactly what we get from this structure. So I'm asking in particular what we get out of having a repeated structure. So having a repeated structure perhaps makes it easier to store those values, which is absolutely an important point we'll talk about in a minute. But it doesn't necessarily grant us any extra ability per se. We could always just store the values even if it didn't have a repeated structure. We always store the values and do the same sort of game. But it is definitely a true point. Yeah?
Would it rather be because we can just do the same set of computations and just loop?
So pretty much, yeah, exactly. So the nice thing here is that if we're doing the same operations, then we're calculating the same derivatives, just with different inputs and outputs. So the real benefit here is that every one of these operations, in the forward pass and in the backwards pass, is just a repeated function. We just do the same function over and over and over again. And this allows us to do an iteration to actually calculate both our forward pass and our backwards pass, which is where we calculate the gradient. So we'll look at that formula and that algorithm a little bit more, but that is the core idea of backpropagation, is we want to be able to calculate it iteratively backwards until we calculate everything. And we'll see. So that's our first benefit, right? So there's three things that we want to improve to make calculating the gradient easier. This is number one. The repeated structure will let us now take this operation, which is this, right? And since we already know the derivative of this, which happens to be this, so that we did talk about this before, but that A is just the output of this entire thing. So it's just sigmoid of WA. Oh, I didn't change the notation here. Dang, sorry. But that's x dot W. Then we get exactly this derivative that is based on that output, right, which I label as A. So we have that. And we can, since we know that derivative, right, remember I said earlier, we can combine things where we already know the derivative. We can combine this into a single operation, which I'm going to call FC here. Stands for fully connected. It is going to be a fully connected matrix multiplication and an activation function. I'm just calling it FC. It's pretty common to call, I mean, you could call it that if you want. It's a weird choice to call it FC, but just bear with me. That's what that means. All right? And we see that we can now make our entire model. We can condense our computation graph and just do a chain of FC computations. So this is exactly the same, and it's including our nonlinearities at each layer. So that's very nice for us because we know how to take the derivative of each operation. We've made the computation simpler for ourselves. Right? And I also want you to notice the fact that we are using the output in here. Right? I've mentioned this a few times, the fact that memorizing the output, and it was brought up by a few people here. It's a good idea. We have the output in our derivative, right? And this is going to lead us to our second good point. We would be wasting a lot of computation if we recalculated all those things, right? So why don't we not? So we can see here now that if we look at some particular, so this is now the function that we're doing, right? This is not including another nonlinearity because we don't like a nonlinearity at the very last operation. But this is going to be our operation here now. And I want you to take some time and try to solve that derivative. All right? So remember, the derivative of an individual FC, right? Try to remember one of those, and this should not actually be that bad. All right? So talk in your groups for a little bit and try to solve it. This is a bit of math for you, but this will essentially be the answer that you need for the homework. All right. All right. How do people feel about doing that math? Is that feeling all right with people? If it is a bit complicated, I'll tell you that the beauty with the computation graph is you could choose to not combine it if you want and just leave it as the other operation, and it decomposes exactly into the correct answer. You could always do that to basic operations, and then just do whatever you are comfortable taking the derivative of. But more or less, I'm giving you the derivative here, and we're going through 2 layers of that. So we should have 2 derivatives multiplied together that look something like this, right? So let's take a look at what the derivative ends up being. And I think actually for this derivative, I did include a sigmoid outside, but you can remove one part of it if you don't want to do that. So we see first, we're just multiplying derivative of A2 with respect to A1, and derivative of A1 with respect to W1. Right? So these are just 2 derivatives that we know how to do from the previous slide. And we look at what we end up with. So first, this is the first, this is actually the first term. So this is dA2 by A1. The reason it's going later is because we need the dimensions to line up. It's a bit of a weird thing, but again, I'm being very proper about the dimensions so that everything here is actually correct. Right? But we're going to have now, so I included a sigmoid if you, or no, this one actually will always include sigmoid. So again, it is basically exactly the same. The only thing that's different is the fact that we have changed out our x for a W2. The only reason being that we're going now, instead of to one of the weights, to the other input. So again, we're just doing a derivative to one of the inputs to a matrix multiplication, and we just swapped them, right? So we just changed that value. The reason it's dot W transpose instead of an x at the beginning is just to line up the dimensions also. Next, the other operation is nearly identical, and this one I did include a sigmoid on that we didn't necessarily need. If we wanted to remove the sigmoid, we would just remove the 1 minus A1 times A1. We wouldn't need that, but if we had a second sigmoid, it's there. And now we just have that it's x transpose times these 2 things, right? And it's essentially exactly just the derivative that we had for a single FC layer repeated twice. We just multiplied them together. We have that there's the x and the w, but that's just because of the direction that we're going out of it. Isn't that neat? Yeah.
Where does W2 come from again?
So it should be W1, sorry. Yeah, all right, so I changed, so this one is W1 and W2 instead of W0 and W1. Sorry.
So it should be W1.
Yeah, so if this was derivative with respect to W0, then that would be W1. So all of the W's subtract one number, and that's our normal convention. Sorry.
Okay.
I just indexed starting at 1, which I think is gross, so I don't know why I did that. Anyway, cool. I hope that wasn't why that this was so hard for you guys. Anyway, so hopefully you can see that you can compose these more difficult operations, and as long as you know the derivative, you can just find the derivative of one of them and multiply them together. It's actually a fairly natural idea. All right? Cool. Now, again, we realize that all of these components in here are values that if we went through and memorized everything as we computed forward, are things we already know, right? So this reinforces this idea that, so 1, we can now combine our operations into just layers where we just compute the derivative with respect to one layer at a time. And 2, that if we memorize everything, we will be able to just immediately calculate the derivative all at once. So there's 2 things that are very important to us. Memorizing them, by the way, is what we do with the cache, if that was not 100% clear. But that is exactly why that's there. So we have this now, and I'm going to add a 3rd layer to it. All right? And let's see what happens when we have 3 layers. So first, let's take the derivative with respect to W2. All right? This is going to be the 2nd layer, right? Index starting at 1. Sorry again. And we get this, right, which is exactly what we'd expect. We go backwards 1 layer, then we go down to the weights, right? That's just the path back to it. And now let's do it for A3 dW1. All right? It's pretty much the same. We go backwards once, then we go backwards again, and then we go to W1, right? So we're just doing now these operations. And anyone notice anything? You two are on it. So yes. What Rushiro said here is that there are things in common. Right? So if we look at these, we will have to repeat these calculations if we were to calculate each derivative individually. And we are a big fan of doing things very fast in machine learning, and repeating calculations is not very fast. So this is our third point now, is that we don't want to repeat any calculations. So we're not going to repeat them when we go to take the values to calculate derivatives. We're not going to repeat them when we go to actually calculate the derivatives. So we don't want to recalculate anything at all. And this gives us the algorithm of backpropagation. And this is all leading up to this core idea. And this is exactly actually what you are implementing in homework 2. And this slide right here is going to have all of the math you actually need to do homework 2. You might not believe me, but it does. So let's look at what we want to do. So first up, we're going to iterate through each of the layers, where L here is going to be the final layer, right? So it's, again, indexing starting at 1. I guess I changed my mind halfway through and started indexing at 1. We start at the first layer, and we go through each layer. And we are going to calculate what the output on this layer is. And we're going to memorize it and say that AI, whatever that is equal to that output. Right? And you see the fact that we are going to be using the outputs from the previous layer to go through. So let's look at what our model looks like. And you may notice the fact that we're using the previous layer's output. But how do we do the first layer? The way we do that is that we call x a0. So a0 is equal to x. Right? So now we can go through here, and we get the output at each layer. Cool. Now we're going to do the backpropagation. So now we want to calculate the gradient. And what we realize is that we can start at the end and go backwards, and we can calculate the derivative of the output of the model with respect to every single layer. Right? We just repeat through these. So we realize that this is actually just the derivative of fc that we've seen before, which is just w1 times 1 minus ai times ai. Okay? And then from that, we can calculate, so we also have to multiply by the derivative up to that point. Sorry, I forgot that was there. So we need to calculate up to that point, right, which we've already calculated. Right? We're doing a for loop. We've already calculated it. And then we just take one more step down the chain. We're just going to do that. All right? And then we realize that this gives us all the information we need to now calculate the derivative of that respective w. So we can find the derivative of AL, which is the output of the model, with respect to that layer's W1, or WI, is just that derivative that we just calculated. I think we've gone all the way back through the chain. We have the derivative of that point. It's just one more step to that W. And all we have to do is multiply the output of that layer times the derivative up to that layer, because we're just doing a dot product. So this gives us a very nice and easy formula to calculate the derivative of each of our w's. And what we realize is we just loop this over. So we go down the chain, and every time we take a step, we calculate both the derivative of that point and the derivative of that w that's corresponding. And we just repeat that. And what we realize is at the end, we can just return all of our derivatives for the w's, and that is exactly our gradient. So this right here, you've probably heard me say that there's only like 10 lines of code needed or whatever. These are them. That's all we actually need to do. Yes?
In the second for loop, like that first line, the last derivative term, why is it I plus 1?
So we're starting from the end, right?
Oh, okay, so we're starting at...
We're starting from the end, and then we're moving backwards. So we start with the derivative that's in front of us, and we move backwards.
Okay.
You may also note that DAL derived with respect to DAL or AL plus 1, I guess in this case, is not defined by us. And what it is exactly that matrix of 1s that is the size of AL. So I guess we'd probably also define that as AL, and we'd start from L minus 1, but it's a nuance that is not particularly important. So that is where our 1 matrix is. And then We just iterate like that. So does this algorithm make sense to people? This is the heart of multi-layer neural networks. So it's a good thing to know. Yeah?
The for loop starting at 1 is actually important because you start with W0, right?
Yeah, no.
You
So
do W0 and then you have to start it at 1 so that you're not starting with W1.
yeah, it depends how you define it. In the homework, it is defined at W0, so it would be 0 to L instead of 1 to L. Yeah.
So how does this work when it comes to the final layer not having a what do you call it, non-linearity?
So you would have to do something to calculate the first derivative that is different than everything else.
Okay.
So you have to do one thing manually, and then you can for loop.
Okay.
Yep. Yeah?
What's the first for loop again? What do we calculate?
So the first for loop is just calculating the output of the model. That is exactly what that's doing, is just going through each layer, and then the final layer is just going to be the output of the model, the final A, and along the way you're just memorizing it. So essentially what you're doing is you're just memorizing all the operations you do along the way, and the outputs of them, and then you realize that when you go take the derivatives, you already have all the things you need to calculate each derivative, each step of the derivative. You don't need to recalculate anything.
So that's like the prediction forward.
Yeah. So yeah, the first for loop is exactly just getting the prediction. It is just running the model, which is wonderful. It would include if we were being if our model also has a loss function, you would also need to include our loss in all of this, in both sides. So it would be our loss would be included at the end of the for loop and at the beginning of the for loop. So we can do the loss stuff in between these for loops, essentially. Yeah. So this is just how we would define derivative of AL with respect to AL. So we just define that as that one matrix because that is what it would be. And that ends up working. Yeah, exactly. You actually don't need to do that in the homework. So I'm going to point out the reason being that taking the derivative of loss with respect to our prediction will give you the correctly sized array. So multiplying them by the one matrix won't matter. You could define it if you want to, but it's unnecessary. Yeah. And one other thing that's pretty nice is we actually don't need to memorize these DALs, DAIs, because we only need them once. We only need them in the next for loop. So we can actually just have a running derivative that is just our current derivative. I tend to call it D out, just as a convention, which is why I call the other one D out. Yeah?
So in the homework we have to store the in and the a, but it doesn't look like we use in here anymore.
Yeah. So storing the in and the a is so that you get the option to either do the derivative like this or as every single operation.
So we're not going to need to use the in the stuff.
You won't need to. Yes, exactly. It's more just the practice of memorizing everything, but in fact you don't need everything to calculate the gradient. Yes? All right? Does this feel good to people? I feel like this should be a little candy for you at the end of this. It's actually a fairly straightforward algorithm to do all of backpropagation. It's just this. Does that feel okay? I know that there's a lot of indices and stuff, but I feel like if you can decompose it, it's actually pretty good. All right. Well, I hope that people like it. It's a good algorithm. Yeah.
For the first for loop, why is it 1 to L and not the other way around?
So the first for loop is our forward pass, is what we call it, where we go through the network the forward direction. We go layer by layer calculating what everything is. And then the next for loop is the backwards function, where we are going backwards through the network calculating all the derivatives. So this is the core idea of backpropagation is we go forward first, calculate everything that we would need, and then do a backwards pass where we calculate all the derivatives along the way. This works really well for our sort of feed forward networks that we have here, where we're just feeding it forward. And it is very useful, and the reason that we have such a repeated structure is so that we can just put a for loop here instead of doing something more complicated. We can do things that are more complicated. It's perfectly possible, but this is just very fast. Okay, cool. Well, now we got a quiz. I feel like everyone loves quizzes, right? Yeah. All right, everyone get someone from your table to come up and grab the quizzes, like usual.
I need to dip, I think like 10-ish minutes. I'm gonna take the quiz to my best and also gonna have 1 minute submitted.
All right, cool.
Thank you.
Yeah.
The page that has like all the office hours in one.
Yes.
Where is that?
So that will be on Piazza and under the resource tab, and then staff, and it should say them all.
Okay, got it.
Yeah.
And also by
All right, you know the drill. This one's going to be a little bit shorter, actually, 10 minutes, because I think it's a little bit less complicated, hopefully. Hey, so someone pointed out to me that I used the old notation in the computation graph. W transpose x is the same as x dot w. Same thing. Another one. It says W0 and W2 should be 0 and 1 or 1 and 2. Yeah, sorry. You can start working with a partner now if you want and talking through your answers. Remember, everyone gets 100 on these quizzes, so it's no big deal. It's not cheating. All right, all right. So that's the end of the quiz. All right. Now, unfortunately, we don't have enough time to do both going over the quiz answers and the thing that I want, which is sad. But I'd prefer to give you guys a little bit of a break and talk about something neat and where we're going in the future with this class. Maybe to let you guys feel a little bit less pressure about this homework. They give you the short answer on each of them. False, false, false. Ooh, yeah. So the answers and proper explanations are on, nice, are all on the slides. And again, a reminder that these quizzes and this material is not messing around. This is real stuff, and this is not easy. All right, I want you to like be okay with that. Your grades will be fine, trust me. This is difficult, that's the point, and I'm not going to just fail you all. That's not what this is for, right? That'd be stupid. Anyway, so that's that, and then if we want to remove the bias, we actually realize if we just add a 1 onto the input, and then make our weight matrix 1 bigger, then one of our weights will exactly act as a bias. It's a very interesting idea, and we can just remove bias entirely, and we can just stop thinking about bias. It's really nice. And this is what all the programs later on that we'll use will do. It's very cool. And for the derivative, really the point I want to make is that both of the derivatives have this common term that are just multiplied by them. So if we switch the derivative, or we switch the loss function, we just change what that derivative is and multiply the entire gradient by that difference, by the proportional difference. So we just divide by this loss gradient and then multiply by a new loss gradient, and then we get the loss derivative, and we get the exact correct gradient. It's very neat. Anyway, you can look at the slides if you want proper explanations to each of these, if it's nagging at the back of your mind. But what I want to do right now is I want to watch a very interesting video about where we're going with the class. And this is a very state-of-the-art paper, and it's very cool. Yeah, you did? Nice. Yeah, I did too. Hey, nice. Lots of people have seen it. Okay, good. So. What we're going to do after this homework, we're going to start being able to use tools that will automatically do our gradients for us and all of that. This is the peak of you guys having to calculate gradients. And we're also going to start working on vision tasks. So we're going to start working with data sets where we can see the data set. There'll be images, and we'll be doing stuff with them. And in fact, we will be generating our own images, a la this face does not exist, and all those things. We're going to generate fake faces, probably. That's what I'm leaning towards. But we'll see what we want to generate. Those might be a little bit too difficult. Anyway, here's a video of some state-of-the-art vision stuff that is super neat.
Dear fellow scholars,
this is a 2-minute papers with Dr.
place that I showed you guys,
or I talked about.
Today, we are going to look at NVIDIA's spectacular new AI that can generate beautiful images for us. But this is not image generation of any kind. No, this is different. Let's see how it is different. For instance, we can write a description and the appropriate image comes out. Snowy mountains, pink cloudy sky. Checkmark. Okay, so we can give it art direction. Make no mistake, this is fantastic, but this has been done before, so nothing new here. Yet. Or we can create a segmentation map. This tells the AI what things are. The sea is down there, mountains and sky up here. Looking great. But this has been done before too. For instance, NVIDIA's previous Gauguin paper could do this too. Nothing new here. Yet. Or we can tell the AI where things are by sketching. This one also works, but this has been done too. So, is there nothing new in this paper? Well, of course there is. And now, hold on to your papers and watch as we fuse all of these descriptions together. We tell it where things are and what things are. But I wonder if we can make this mountain snowy and a pink cloudy sky on top of all things. Yes, we can. Oh wow, I love it. The sea could have a little more detail, but the rest of the image is spectacular. So, with this new technique, we can tell the AI where things are, what things are, and on top of it, we can also give it art direction. And here's the key, all of these can be done in any combination. Now, did you see it? Curiously, an image popped up at the start of the video when we unchecked all the boxes. Why is that? Is that a bug? I'll tell you in a bit what that is. So far, these were great examples, but let's try to push this to its limits and see what it can do. For instance, how quickly can we iterate with this? How quick is it to correct mistakes or improve the work? Oh boy, super quick. When giving art direction to the AI, we can update the text and the output refreshes almost as quickly as we can type. The sketch-to-image feature is also a great tool by itself. Of course, there is not only one way, there are many pictures that this could describe. So, how do we control what we get? Well, it can even generate variants for us. With this new work, we can even draw a piece of rock within the sea, and the rock will indeed appear. And not only that, but it understands that the waves have to go around it too. An understanding of physics, that is insanity. My goodness. Or, better, if we know in advance that we are looking for tall trees and autumn leaves, we can even start with the art direction. And then, when we add our labels, they will be satisfied. We can have our river, okay, but the trees and the leaves will always be there. Finally, we can sketch on top of this to have additional control over the hills and clouds. And get this, we can even edit real images. So, how does this black magic work? Well, we have 4 neural networks, 4 experts, if you will. And the new technique describes how to fuse their expertise together into one amazing package. And the result is a technique that outperforms previous techniques in most of the tested cases. So, are these some ancient methods from many years ago that are outperformed, or are they cutting edge? And here comes the best part. If you have been holding on to your paper so far, now squeeze that paper, because these techniques are not some ancient methods, not at all. Both of these methods are from the same year as this technique. The same year. Such improvements in less than a year. That is outstanding. What a time to be alive! Now, I made a promise to you early in the video, and the promise was explaining this. Yes, the technique generates results even when not given a lot of instruction. Yes, this was the early example when we unchecked all the boxes. What quality images can we expect then? Well, here are some uncurated examples. This means that the authors did not cherry pick here, just dumped a bunch of results here. And, oh my goodness, these are really good. The details are really there, the resolution of the images could be improved, but we saw with the previous Gauguin paper that this can improve a great deal in just a couple years, or with this paper in less than a year. I would like to send a huge congratulations to the scientists at NVIDIA, bravo! And you fellow scholars just saw how much of an improvement we can get just one more paper down the line, so just imagine what the next paper could bring. If you are curious, make sure to subscribe and hit the bell icon to not miss it when the follow-up paper appears on 2-minute papers. What you see here...
So, I'll make a point here about the class. The reason that we're running now, and we're moving so fast, and we're trying to really cover this stuff and kind of push you in the deep end, is so by the end of the semester, we can be there. And talking about how that works. And maybe in your final project, doing something like that. So hopefully, maybe that contextualizes why we're doing it the way we're doing. And as soon as homework 4, we are going to be generating our own images. So, again, I say, eat your vegetables, and we can have dessert, okay? And most of the semester will be about this stuff once homework 2 is done, once you guys are strong in this. All right, well, enjoy your week. Go. Bye.
So, about the homework 1 and
Yep.
2 update, I've been watching videos this week, and I'm wondering if I could submit both homework 1 and 2 next Tuesday.
Next Tuesday.
Yeah, would that work?
Okay.
I'm halfway done, and I want to take a long weekend to
Yeah.